Hello everyone. We hope you are enjoying this annual meeting so far. My partner Juan Sebastián Bermúdez and I, Kevin Giraldo, are senior students in biomedical engineering at University of Los Andes, Colombia. Today we are going to present you our work in liposomes encapsulation of therapeutic nanobioconjugates enabled by microfluidic devices, aided by mathematical models using COMSOL Multiphysics. As you may expect, this work aimed to study, understand, and examine different approaches and configurations of microfluidic devices to encapsulate nanobioconjugates within liposomes. First, we have to introduce our first big concept of drug delivery systems, which allow to focus bioactive molecules to a specific target, hence increasing their bioavailability and stability under harsh conditions. Especially, this has been used and bossed to deliver pharmacological compounds to treat different conditions such as cancer, neurodegenerative diseases, and even to control antibiotic resistance. Liposomes have been particularly attractive for these applications and for biomedical applications due to their low cytotoxicity and immune response, and because they are suitable to transport molecules across the blood-brain barrier. Nevertheless, there is one major challenge of liposome synthesis and generation, which plays an important role on active molecules stability, and it's the homogeneous distribution of the size or size polydispersity. And this has been optimized in our research group. And besides, we have successfully encapsulated self-penetrating molecules in liposomes. So these molecules are known as translocating molecules such as outer membrane protein A, or commonly known as OMPA. And this protein is present in Escherichia coli and has surfactant properties which allow to spontaneously cross the lipid layer of liposomes and cells, and they are used in drug delivery systems. So considering these aspects, our goal is to establish a standard procedure with high reproducibility using microfluidic devices to successfully encapsulate nanobioconjugates within liposomes.
With the same, it is important to illustrate the potential of microfluidic devices for the transfer of liposomes and nanobioconjugates. Therefore, the second big concept here brings up the features of microfluidic systems. Microfluidic systems can be used for different purposes, such as mixing, separation, screening, and drug delivery systems. Generally speaking, these systems can be classified according to the use of external power supplies. On the one hand, we have passive mixing microsystems, which just rely on fluid mechanics and convection and diffusion phenomena. Also, due to the small size of their microchannels, we just rely on laminar flow patterns most of the time. On the other hand, we can have active mixing methods. These methods are based on introducing energy sources such as magnetic field or ultrasonic waves to alter fluid particle dispersion, fluid streamlines, or even mixing processes. Another key concept here is the geometry, which can be used for changing the fluid patterns, flow patterns. For instance, chaotic advection can be induced by introducing C-shape units in a serpentine micromixer. Also, we can take advantage of microfluidic hydrodynamic focusing for colliding two or more fluids within a single microchannel. This can be used for generating specific fluid streamlines or even for producing liposomes by the disruption between dispersed and continuous phases. Ultimately, we have been doing research in active mixing methods related to the use of acoustic fields. Some of the existing literature has shown that introducing acoustic fields as an energy source allows to introduce acoustic streamlining flow patterns, improve flow focusing, and also improve the interaction between different fluids.
Basically, by using external power supplies of ultrasonic waves, we are introducing energy in the system. And this has been used in application of acoustic streaming to control the particles trajectory in a fluid, and in other studies that report that this method allowed to generate some operation in liposomes membrane. Nevertheless, the implemented mathematical model in this work does not consider these. And well, here we have to consider that for ultrasonic manipulation applications, the frequencies used are greater than 20 kilohertz. So by considering piezoelectric devices and transducer, we hope to, and we expect to increase the mixing and the interaction of both molecules of interest suspended in fluids within the microsystems.
So with that in mind, we want to answer the following question. Is it possible to enhance mixing of fluid phases to improve liposomal encapsulation of nanobioconjugates by translocation? Well, in order to answer this question, we want to target the following 6 ideas. The first one, we want to consider an easy and affordable active mixing method with ultrasound. So, in order to achieve that, we considered ultrasonic baths, which are available in most laboratories. We also consider a typical micromixer with chaotic advection for improving mixing processes. We also consider a low-cost microfluidic device, which can be manufactured by techniques such as laser cutting, 3D printing with polymethyl methacrylate. In order to study the interaction between lipid solutions with liposomes and ferrofluids with nanobioconjugates, we rely on computational studies for method validation of acoustic streaming by studying the microscopic interaction of liposomes and the nanoparticles suspended in aqueous solutions.
Regarding the methodology, we use COMSOL Multiphysics software to implement the computational model, using and considering 3 multiphysics approaches. So first we have the acoustic piezoelectric interaction, then the thermoviscous acoustic in a frequency domain, and finally the mixture model and laminar flow. Each one with a corresponding solver and a study type of when the 2 first ones, we have the frequency domain solvers, and the last one in a stationary study. Considering these, the governing equations have or are followed as present here. So first we have the piezoelectric effect given for the ultrasonic bath, and this part allows us to module the disturbance of the medium that goes first to the liquid of the bath, then it goes to the device to finally get to the into the microfluidic channel. And well, parallel with this disturbance and waves, that is basically the same effect that it has a sound stereo has. We can considering the effect of the energy dissipation of each field. So to this we consider the thermoviscous effect, and this allows us to convert the energy and calculate the external forces that will affect the behavior of the fluid and the particles or the compounds within. With this, the acoustic pressure and the energy density, we can solve the whole energy density equation, and this is a key part of the application of this application, due to that the energy is integrated in the area and calculated the overall medium energy to further apply Newton's second law and calculate the overall fluid forces and introducing into the Navier-Stokes equation. So with this, we make sure that we consider the force in a microscale and in a microscale.
So in order to validate our active mixing method, we developed 2 different computational approaches. The first one, a passive mixing model with the mixture model laminar flow interface, and the second one, introducing the thermoviscous acoustics and piezoelectric interaction as explained before. In this case, we consider 2 different ultrasonic bath configurations, one with 37 kilohertz and the other one with 45 kilohertz. we also had to consider the sound attenuation and sound velocity related to the acoustic interaction with the microfluidic device material, which refers to PMMA or polymethyl methacrylate. The corresponding geometry for the microfluidic device is shown here. As you can see, we consider a typical serpentine micromixer with C-shaped repeating units, two inlets, one for the ferrofluid, the other one for the lipid solution, and a mixing chamber of 840 micrometers. Also, we introduced both ultrasonic baths with a 2D approach as shown here. The first one an Ultrasonic P30H, the second one a Bransonic S30, both baths with different acoustic pressure fields. And on the right side, you can see the coupling with the microfluidic device. The boundary conditions are shown here for the mixture model. We have the two inlets, one for the dispersed phase and the other one for the continuous phase, referring to both fluid phases of interest. And on the right side, we can see the acoustic structure boundary and the electric potential introduced for modeling the effect of acoustic fields.
So regarding the results, we divided into the passive mixing encapsulation and another mixing, but using ultrasonic manipulation due to acoustic fields. At first, we have to make an hypothesis, considering that by increasing the mixing, we are going to increase the dispersion of the particles and hence increasing the interaction between both compounds. So we are considering that the interaction between liposomes and nanoparticles will increase, and then the encapsulation. So as can be seen in the figure, the passive mixing and encapsulation is only achieved until the 5C unit. On the other hand, introducing the acoustic fields implementation of both Elmasonic and Bransonic, we found that even though both ultrasonic baths manage different frequencies, the field pattern or the acoustic pressure field pattern within each microfluidic device is the same. So the amount of energy will be the same for both. So the interaction and the disturbance will be same.
So here you can see some of the current results we got from the ultrasonic manipulation model. As you can see, there is a change in the volume fraction dispersed phase surface. This has to do with the implementation of the acoustic fields. So in this case, you can see that the full mixing and corresponding interaction is achieved just after the second C-shaped unit, which is way before than the passive mixing model. Here is an overview of the comparison between the results of both models. On the left, you can see the passive mixing model, and you can see that after the third C-shape unit, we haven't reached the full mixing pattern we expect. But on the acoustic field model, after the C-shape unit, as you can see the mixing pattern.
So the explanation of this behavior can be given by considering that the normal particle trajectory patterns are accordingly with the streamlines patterns. When we introduce the energy given the ultrasonic bath and the sound pressure waves, it's generated a multidirectional vector force within the microfluidic channel. Then this decreases the velocity of the particles and increase the dispersion of the particles because it's change the streamline patterns of the particles. So considering that by applying acoustic fields, the dispersion will increase, the mixing will increase, and hence, according to our hypothesis, the encapsulation will increase. So this model allow us to identify that by applying external forces or energy source, the encapsulation will increase.
Okay, so some final remarks we can make here are the following. The first one, we found out that although the computational model suggests increasing on liposomal encapsulation by applying acoustic fields, we need further experimental validation for that. On the other hand, we expect to improve our models by considering the transfer of chemical species, including an irreversible chemical reaction, which can actually estimate the liposomal uptake of nanobioconjugates with and without acoustic fields. So this is our team. We want to thank you all for attending this presentation today. If you have any questions, you can let us know in the following Q&A section. Thank you so much.
Thank you.